Hello, guys, and welcome back to Chapter 4, Week 4, and this is going to be our third video. So in this video, we're going to talk about memory access modes. Okay, so that is the focus. We already know the move instruction. We know the arithmetic plus the flags. So now we want to talk about memory. Okay, how data is accessed in the memory. Okay, because we talked about moving and adding and subtracting, and that requires moving things in and out of the memory. So how the memory is really accessed? Is it direct or indirect? Okay, so we're going to talk about these, and then we're going to talk about the operators as well, some important operators. So when we talk about memory, like the one right here, okay, so always try to use your hand. Okay, so this is the array B, or the list 10, 20, 30, 40, right? So this is what we call offset. So every time you say move to AL, since this is a memory byte, array B, you are only gonna move 10. You will never be able to access 20 this way. So what if you wanna access 20? If this is the address that points at this whole space, if this is my reference point, I can offset from it. So offset means what? A reference point fixed. And you can move either by 1 from here, or you can move by 2, or maybe you can move by 3, and so on and so forth. But always you adding from here, plus this, plus this. So you are referencing to this point. So this is a fixed point. Okay, so the offset. Offset means you're adding a specific amount from this fixed point. So if we say here, move to AL array byte, it's by default, it knows only 10. But if I want to access 20, I will say this offset, add 1 to it. This is 0. So you can say offset array B, okay? Or you can say offset it with 0. That means stay where you at. So these are both the same. Okay, it's gonna move 10. But what if we're gonna move this value? Then we're gonna add 1. So we move 1 from here, we're gonna go here. We move 2, we're gonna go here. We move 3, we're gonna go here, and so on and so forth. So you can reference your point or your memory in this way. Okay, so what if we're gonna say move to AL array B plus 3? So the AL right here is gonna equal to what? 40. You see what I'm talking about? So you are offsetting. This is the way we access the memory, direct offset. Why we say direct? Because you are using the memory address, the fixed point, and you add to it directly. Okay? So you're gonna see the effect of this, okay? So keep that in mind, all right? So again, if you have the square brackets, that means nothing, okay? Just the same thing, just explicitly. Why doesn't array plus 1 that actually did not produce 11? You see what I'm talking about? So when we say array byte plus 1, so array byte refers to 10, right? When we say add 1 to it, why doesn't add 1 to it? So what I'm trying to say right here, isn't this like saying add to array byte 1? No, it is not. That is different. That's an instruction. So this is not an instruction. Remember, this is a directive. And if the directive seen right here, it sees an address, it knows that this is what? An offsetting. This is known by the assembler. Because you might also say move to AL 1 plus 5. So this is not an address mode. This is gonna evaluate the expression, and this is gonna be 6. You with me, guys? And then it's gonna move 6 to AL. The reason why this does not happen right here, it's not gonna add 1 to the array, because by the assembler, this is gonna be known as what? Direct offset operands. Because memory address and a directive, plus or minus, and an immediate, that is gonna be right away. Do not change the content, just offset from that reference point, okay? All right, so this is another memory. I would like to always learn how to draw memory, so that way I'm gonna master it. So it's gonna be array W, and I know now my memory is gonna be divided by 2. So this is 1 block. This is the second block. This is 1, 2, 3. and this is the third block. So here I'm going to have little Indian right to left. So I'm going to say 0, 0, 1, 0. That's block 0. And then here right to left, 0, 0, 0, 2. So little Indian doesn't mean change the order of the list, right? And then right here, we're going to have 0, 0, 3, 0. So this is 2, this is 4. So the offset right here, skip 2. So that's 0, 1, right? 0, 1, right, in terms of byte. But skip 2 bytes and you're going to be here. So this is 0, 1, 2. So in fact, that's why we call it 2. This is 3, 4. That's why we call it 4. That's the beginning. So that's the reference. Start reading from here. You see what I'm talking about, guys? Okay. So if you say array W plus 2, it's going to move this part. And remember, when we're going to say it moved this part, this is a register AX, right? And this is AL, and this is AH. So when we say plus 2, it's going to read the first byte, because that is the 2. So it's going to put it in the right, because this is 0 to 15. And then it's going to do what? To 0. So that's why it's going to see it in this way. So try not to write it left to right. Write it just really right to left. So you know how to read from memory to register. And when you get it from register to memory, it should go in the same way as well. Okay, I'll explain. I already explained that in the previous lectures. All right, so what if you say plus 4? Plus 4, you're going to start reading this block. That's the beginning of this block. This is 4. So why you did not say 4 and 5? If you give it the beginning, it knows it's a word, so it will read this byte and the following byte and will stop. So just tell it the beginning, because the semantic here says is what? Word. How about this memory? Let's draw it. Let's draw it right here. So this is array D. And now we're going to have 1, 2, 3, 4. That's one block. 1, 2, 3, 4. That is the second block. And then 1, 2, 3, 4, that's the third block. And then 1, 2, 3, 4, right? That's the fourth block. So 1 is going to be stored like this, 0, 1, 0, 0, 0, 0, 0, 0. Keep that in mind. And this is 0, 2, 0, 0, 0, 0, 0, 0. This is 0, 3, 0, 0, 0, 0, 0, 0. This is 0, 4, I'm sorry, 0, 4, 0, 0, 0, 0, 0, 0. So this is block 0. This is block 4 because we're moving with a D word. This is block 8. This is block what? 12. You see it? So if you look at it here, this is 0, 1, 2, 3, 4. So that's why we call it block 4. This is if you go 5, 6, 7, 8. That's why it's 8. It's 9, 10, 11, 12. That's why we call it 12. Do you see it? So that is the whole block. So if you know the beginning, that is the offset, that is the fixed point, and you add 4 to it, you are right here. Since it's a D word, it's gonna read this and move it to EAX, byte by byte. It's gonna take what? 0, 2, you with me? And then what? 0, 0, 0, 0, 0, 0, and it's gonna stop right here. Why? Because it knows from the semantic, it goes from here 4 bytes. It means the total 4 bytes. Add 3 bytes to this and get out. You see what I'm talking about? So the details are very important right here, guys. All right. So that's what you're going to see right here. So you should always write the memory and try to get it from here to there. Try not to store. If you want to move, just play with this example. You're just going to say move into A1. Just create, let's just say A2, array a space in the memory, and move EAX to it, and just declare A2 as a D word and question mark. So now when you read this to this memory, the A2, it points at 4 space, right? So when you read this, you're going to read right to left, right? This is 0 to 31. So it's going to be 0, 2, and then 0, 0, and then 0, 0, and then 0, 0. Do you see it? So now you get it from register to memory. Here you get it from memory, which is this part, to register, which is this part right here. Okay, so this is what we call direct offset. All right, so what happened if we go with the minus? What if you go negative? Is negative something that is acceptable? Okay, so let's look at that. Let me erase the board right here. I mean the slides. Okay, so let's look at this part. This is very important. Okay, So here, what if we say array W, which is this array, and we say -2? What if we say, is this correct? First of all, if this valid, is this also valid? We're going to say plus 16, but all we have here is 12, right? So 12 plus 4 is going to be 16. So do we have something stored in this part? We don't know. We did not store anything, but it could be something in there. Can we move this content right here? Yes, it's your own memory. You can move it. Is it possible that we're going to move a garbage? Yes. So how about array W -2? You are right here, and you are going up now, because plus you go down, minus you go up, plus you go down. You see what I'm talking about? So if you're going up 2, then you're going up right here. What do we have in here? We don't know. Whatever you have in here is going to be red if you want to move it. You see it? If you want to move that to EAX, whatever we have, that's why I have the question mark. You're going to move it right there. So these are valid. So try to play with it. Create your own memory. And my advice, draw your memory. Okay, so if let's say if I can go with it right here, I might have before this memory, maybe right here. Okay, guys, I will do it right here. Right here, maybe I'm going to have a memory. Let's say I would have, let's say A5, and then I would say it's a word. Let me just make it very simple. And I have 1516. So if this is 1516 as a hexadecimal, then I know that here I'm going to have 16 and here I'm going to have 15, right, guys? I'm sorry, it's the other way around. Let me change the color. Okay, let me see if I can put the green. Okay, so right here, I'm going to first read the 16, right? So this is going to be 16, and this is going to be 15, right? So if we say this W -2 to AX, then this is going to be your AX, and AX right here is going to be what? 1615. You see what I'm talking about? This is the part right here. Okay, so you don't know. You're going to go -2 to the top, and you start reading from there. Okay, and always when you read from an offset, you're just going to go based on the spec right here. If the spec says 2 words, start from here and only read 2 words. If it says the spec says 4 words or 4 bytes, then just start from the offset and go 4 bytes. That's it. Okay. So this is what I was talking about. If I were you, I would just go ahead and try to draw this memory. And right here, we're talking about this memory. So this is going to be the space you're going to have. So you're going to have first 80, and then you're going to have 66, and then you're going to have A5. This 0 is not going to be stored, right? You know, this is just for the assembler to know that without it, we're going to have a problem with A5, because that's going to be maybe a variable name. All right, guys. So if that is the case, that is the memory that my byte points at. So you can offset it. You can read 80 right away, or you can offset it. Okay. So you can add, maybe you can add this to this. Okay, because you have already this in AL. So now instead of AL having 80, now it's going to have 80 plus 60. So AL now is going to have what? It's going to have 14, right? 140. Okay, and then you're going to add 2. So this is 0, 1, 2. The reason we are moving by 1 and 2 because it's a byte memory. If it's not a byte memory, you might say 0, 2, 4 if it's a word, or 0, 4, 8, and so on if it's a D word. Okay. So keep that in mind. What is your evaluation of the following code? Okay, is this something okay? Can this work? Wait a minute, we are adding what? We are moving 1 byte to AX, right? Is that okay? Play with it, please. It should not, right? Because this is mismatch. We are moving small to large, and we are adding small to large. So you should get an error right here, right? So play with this in Visual Studio and see what happens. Okay. Any other possibilities? Think about other ways, okay? All right, so this is what we call direct. So direct means you have a, like, just me change this. Let's say this is variable 1 and points at 5, and you're just gonna move it directly to AL move V1 directly. I can go to 6 if I say AL V1 plus 1. So this is direct. This is direct with offset. Now we're trying to play with the indirect. Okay, so why we need the indirect in the first place? Why just not go direct, okay? I'll explain that in a minute. But before we can do indirect, because indirect requires that using an operator is known as an offset, right? So we have to use the offset operator. Okay, so if we want to use the offset operator to do the offset, to do the indirect, we need to understand first how offset works, and then I'll explain to you what I mean by the indirect, okay? And why the indirect. So when we use the offset, offset is a function, okay? It either works on 32-bit, return a 32-bit address, or return a 16-bit address. So if you want to know the offset, where this val is pointing at, if you want to know the address, remember the reference, because val1, it is a 32-bit address, right? If you want to return this address, you just use the offset. Why I need to return the address? Because you want to access the memory indirectly. Why I want to access the memory indirectly? I will answer that later. But right now, I want to show you how can we get the address that represents val1, okay? So we are going to focus in this part, all right? So let's move on to the next slide. So in this slide right here, if you can see, this is your memory. So this is bval, which is a byte. This is wval, which is a 2-byte, right? So this is 1, this is 2, and this is 4, right? And this is also 4. This is actually the address of this byte, the bval, okay? So if you say offset of bval, ESI is a register that is heavily advised to be used to hold the memory address. So the bval now is going to hold the address, not the value. Do you see it? If we have, let's say, 5 in here, and we say move, we are not moving 5, we are moving the address. Okay, so offset, it doesn't care about what's inside here. It cares about what is the address. It's going to return the address, and we're going to assign it in this way to ESI. You see what I'm talking about? If you need this address, you just go by 1, right? So you're just going to say offset wval, right? So wval is just going to go 1. So it's going to this address plus 1, right? So you're going to be here, and that's what you see it. If you're going to go from this fixed point right there, it's going to be 1 plus 2. It's going to be 3 bytes. You have to cross 3 bytes, and that's 3. You see it? If you want to go further and you go to the 7, you see it is 3 plus 4. You're going to go to here, right? Which is the 7. So the bottom line that offset always going to return the address. Why we need the address in ESI, I will show you that. But now we need to know that we need the address. We don't need the value inside here. Let's say 5, 20, or 19. I don't care. All I care about, I need the address. Why? Because we need to access the memory indirectly. Why that's important? I'll explain this just in a minute. Okay? So these are like some like basic examples right here. Let's look at this example right now. So right here, if I say move, this is move, right, to ESI, right, the offset of the array plus 4. So the array plus 4 is going to be this, right? You with me, guys? This is 0, this is 2, this is 4, this is 6, this is 8. Why? Because this is a word memory. So what we're going to have in the ASI is the address that points at 3, I'm sorry. Okay? So it's going to be the address that point at 3. So if the beginning of the memory is this address, okay, so we're going to add what to it? 4. So if we're going to add 4 to it, we're going to be right here. Okay, so that's 0 to 4. So we're going to get the address that points at 3. At 3. We are not interested in 3. We are interested in the address that points at it. You see what I'm talking about? Okay. All right, so if you want to look at how this offset works in high-level languages, if you know C or C++, you might have looked at pointers. Pointers are very complex, at least their syntax in C, because they're telling you to use the star in here, and this is a variable name, and it's very confusing. But if you look at it at assembly, it's really straightforward. So you have an array right here, okay, and you want to get the pointer. The pointer means what? The address that points at the first cell in this memory, or the first value in this memory. Let's say it has multiple value. I need the address. I don't need val1. I need the address. So if you want to do this in assembly, you just declare an array and you offset array and you assign it to ESI. instead of using this sign, okay? So now ESI, it has the point. So the pointer in C points at this and val1 points at this. So you have two pointers at the same value, right? Either you can use the variable name or you can use the pointer. When you are using the pointer, you can do a lot of things. You can do a lot of offsetting and you can access the memory more efficiently. Okay, but this is how, if you want to think about it in a high-level language, the usage in a high-level language. So let's think about the indirect. Now we know the offset, and we know the offset is going to return the address. Now we want to think about the indirect, because without the offset, it is a little bit challenging to do the indirect, but I will show you another way to do the indirect without the offset. Okay? So let's look at this example. So my question right here, I'm going to answer it, which is why we need indirect. Okay? So let's imagine you have GSU, right? You want to go to GSU and you live somewhere in Atlanta. Okay, let's say you are in Alfreda. Okay, so if you go to the GPS is going to tell you there is a route that is going to take you 30 minutes, and there is a route that is going to take you 70 minutes. Okay, so in terms of time, which one is short? Is this one. But if you look at the distance, this is maybe 15 miles, and this one may be 6 miles. But that's shorter, but it takes a long time. Maybe this is a heavily used route, right? Many people use this route, so the traffic is a problem. So maybe indirect, if you go a long distance, indirect, you might be there in less time, though you have to drive longer distance. Do you see what I'm talking about? So the route is longer, but shorter because you don't have to wait. Here, it's not about short, it's about the traffic here. You're gonna wait most of the time, okay? Had you have not had the traffic in the first place, you would be there in no time because it's very short, 6 miles. You see it? So the same applies to the memory. If you access the memory with variable A, let's say 5, this direct sometimes is very expensive. Okay, it's better to access the memory indirectly, and I will tell you why. So why indirectly is very efficient? Remember that there is a price we have to pay every time we go out for from the CPU to the memory. If this is the CPU, remember the wasting cycle. Every time we go there, the CPU is faster and the memory is slower, and then we have to wait. So that's a wasting cycle, right? So if we go outside once and we get the address of the memory and we keep the address here. So every time we need to refer to this A, we're going to use the address here, so we don't need to go outside. Because every time you see A, the computer is going to fetch, decode, and execute it. Because it doesn't know, it cannot remember. It doesn't have intelligence like us. Okay? So this is one way to add efficiency to the computers, just to go with the offset of val1. So we're going to take the address that points at here. If we say val1 plus 2, we're going to take the address that points at 20. So we took the address right here, and remember, this is a must use. So when you say ESI, it's a 4, right, guys? It's a 4-byte register. You agree with me? That's ESI. Go to chapter 2 if you forgot what this register is all about. But wait a minute, isn't that 4-byte register? Aren't we moving 4-byte register to a 1-byte? Isn't that a mismatch? You see what I'm talking about? But in fact, this is here, you are right, it's a 4-byte register. But when we add the square brackets, we are adding semantics. So we are not interested in the value stored right here. Just imagine the address here is 00, 00, 01, 04. So the address right here is going to be 04, 01, 00, 00. We are not moving the address. We are moving what the address is pointing at. And the address is pointing at what, guys? It's pointing at 10. And 10 is of size what? Byte. So that's fine. We are moving a byte to a byte. So that's going to confuse you in test 2. Keep that in mind, and maybe in the final. So you need to know that the indirect, you should know that at what space that the indirect is pointing at. What is the space? Is it a byte? Is it a word? Because if we take these square brackets off, then this is mismatch because you are moving the address, which is 4-byte to AL. That's mismatch. But if you put the square brackets, the assembler knows that, hey, you are pointing at a memory. So we are not moving the address itself, we are moving what the address is pointing at. Okay? We're going to do a lot of tricks if we know this. Okay? Very well. So, and if we want to move 20, so all we need, we say what? Increment ESI. So ESI is going to be what here? 0, 1, and then it's going to be 5. So this is going to go here. This is 4 plus 1 is going to take you here 5 because it's a byte. We incremented, and then now we are moving what? To AL, we are moving 20. You see it here, we moved 10. We're going to increment it again, and then we are moving what? So now this is going to be 6. Okay, and then when we do this one, then this is gonna move, what is gonna move 30. Do you see what I'm talking about? So when we go outside, we go to val1 and we fetch it. Then we store it in ESI. And you know, ESI is inside what? The CPU, right? So the next time when you say increment ESI, do we need to go to outside and figure out what val1 is? No. And that is the idea right here. There is no memory waste time. Okay, there is no wasting time to go and access the memory because you already have the address inside the CPU, just gonna increment it. Do you see it? So indirect is faster. Why? Because you don't need to go outside and waste like number of cycles every time you want to access this list. You see what I'm talking about, guys? I hope so. Okay. So this is going to be 30. So keep that in mind. And every time you increase, now the address is pointing right here. Remember, ESI is no longer pointing at 10. Now that is the whole thing. Okay. So the offset just gets you this address and you keep changing it. That is changing the real reference every time you say increment. Okay. So this is one part, and this is if it's a word, the same thing. So if this is word, I will draw it. Always, guys, try to have this habit. 0700. Even though I don't have the 00, but this is a word memory. Declare this in Visual Studio, and you will see what I'm talking about. 0300. If you want to do well in this class, you have to do this way. Okay, 0200. So this is 0, this is 2, this is 4 because it's a word memory. So here you say the offset of my count. Then you are taking the address that points at here. So I no longer need my count because I have its address. It's already in ESI. And if I want to access the ESI, I can do it. So keep that in mind. This is ambiguous now. Okay. So if you're going to say increment ESI, that is you are moving by 1 byte, right? That's okay. It's nothing problematic. But you are not going to move by what you say here is memory, right? What your memory here is, it's 0, 2, 4. But now you are moving by 1 because you are incrementing. You know, increment always add 1, but here we need to move by 2. So that's confusing. So we better say what? We better say add to ESI what? 2, because this it should not be used, just should be used with a byte. Okay, so keep that in mind. The size of the operand may not be evident. Okay, so just keep that in mind. All right, so if that is the case, then let's look at the indirect. Now you'll see the power of the indirect. So we're going to get the offset, the address of the array, and this is your memory. If I were you again, I would draw it 0010, that's the first part, and then 0020, that is the second part, and then it's going to be 0030. I'm sorry, that is going to be the third part. So this is going to be 024. Always do it that way. So you're getting this offset. You are moving 10 to EAX. So sorry, to AX. So first you're going to read 00, so that's going to be 00, and then 10, so that's 10. Okay, and then you're adding to ESI too. So this is your address. Okay, so you are adding to the address because you took the offset. Let's just imagine this offset was 000004. So if you add 2 to this, is going to be 6. Then you are pointing here. So that's what you did. So you are incrementing this to the second part, and you're adding this now to AX. Okay, and then now you increment it again by 2 because now the offset is pointing here. You add 2 to this, you're going to go to this part. You see what I'm talking about? So this is going to be what? 4 plus 2 is going to be 6. 6 plus 2 is going to be 8. So you're moving by 2. So this is 024. Do you see what I'm talking about? So this is how the offset works when it's a word memory. Okay, and this is faster. So only thing you need to go outside only once. Get the memory address, assign it to ESI. ESI is inside the CPU, and you don't need to go outside anymore. This is going to be indirect. That's why indirect is better than the direct in some situations, especially array and lists. So this is the indirect operands. I would show you another way to access the memory indirectly, okay? Without the offset, okay, but using pointers, okay? But before we do that, let's look at the index operands. Okay, so if you look at the index operands right here, so it's the same thing. You're accessing the memory, okay, without offsetting with an immediate. Okay, so instead of saying array plus 0, you say array plus ESI. Why? Because 0 is an immediate, and immediate is in the dot code, and the dot code is a memory, and every time you go outside, you're going to waste the time. So you're just going to do it once, and you add it to ESI, and then you're going to always offset with what? With a register value. If you offset with a register value, then you're doing what? You're doing index operand. This is how you're going to access the memory. Okay, this is the second way. So we know direct with offset, indirect, and we know what? Index operand. Okay, so if you do this part right here, you do it here, and then now you can say it either in this way or in this way. This is very close to what you guys do in Java or in C, okay? So these are alternatives. So now you're going to say add to ESI2. And then now you're going to, this is going to save you a lot of time. So now instead of saying array plus 2, you're going to say array W plus what? Plus ESI. So that's the idea of the index. So these are the two forms. Either use this form or this form. I am a big fan of this form because it's very precise, okay? So what do you need to do if you want to declare this memory as a D word? So the only thing that you need to do instead of adding 2, you're going to add what? You're going to add 4 because it's going to be a D word memory, right, guys? Okay. All right, so we can also, because when we use the offset, we are actually using a method, guys, right? So it's going to take time to call this function and to load it, and it's going to take a lot of time. Can we get rid of using offset? Instead of saying move to ESI, the offset of A, let's say A is a byte, and it has a 5. So we need the address of A. That's 5, 6, 7, and so on, okay? The reason why we use an indirect, because it's a list or an array, and we only need to go once out, and then after that, we're going to just save wasting the time and go to that register right away and keep accessing the memory, right? So if we want to get rid of offset right altogether right here, can we do it? Can we get rid of this function? Because calling this function is going to slow your program down. Can we get rid of it? Maybe we're going to use pointers. Okay, so let's look at what a pointer is. So right now, let me go back to this part. So now we know A is pointing at this memory, right? So I can actually come here and say B is, I would say Y, it's a D word. B is a D word in A. Interesting. So I'm declaring B as an A. But A is 5. Am I assigning 5 to B? No. If you say A in the dot data, they are not going to assign the 5. They're going to assign the address to B. So if B is a D word, it is going to have a space of size 4. You guys with me? 1, 2, 3, 4. You with me? And just imagine if A here is has the address. That's the D reference. Remember, 0000. Right, 02. Just imagine if A is dereferenced in this way. It has the real address 02. Okay, 00002. So in other words, now you are storing in B what? You are storing 02, 000000. And so B is a pointer. Why? Because it stores an address. It does not store a normal value. It stores an address. So that's why we call it a pointer. So if you want to access 5, 6, or 7, you can either use A or you can use B, because B is a pointer that points at 5, because this is just the first value. You see what I'm talking about, guys? Okay, so this is what the idea of the pointer is, okay? So we can do that, but before we do that, let's just look at the PTR. This is another part of the operators that is very important. So now we know how to declare a pointer. We can also now use a PTR to access parts. Okay, so what in this memory if I just want to access this part? Okay, but this memory is a D word memory, but I just want to read this and assign it to, let's say, if I want to read these two and assign them to AX, we know this is incorrect, right, guys? You know, move is going to say mismatch because this is what? This is 4 byte and you're moving it to 2. This is impossible. But all I'm trying to do, that's why we said an error. All I'm trying to do right here, I'm trying actually to read what? 1, 2, 3, 4. If I want to do this, I can use what? I can use the PTRs. Okay, so if I want to use a PTR, the good thing about the PTR, I will actually tell you what I want to read. I want to read a word, PTR, and then I give you the variable. I will show you the declaration in a minute. Okay, so that is going to be very important. So what I said, I'm reading a word, PTR, start reading from where? My double. So if you look at this double right here, it's going to be stored in this way, if you agree with me. 7, 8, 5, 6, 3, 4, 1, 2, right? Because it's little endian. So right here, what you're trying to say, you are actually saying, I want to read these 2 bytes in this statement here. It's not in my statement, in this statement. So when you do this, you said, I want to read the word, the first word right here. So that's fine. If you do this, moves said, I'm okay, because I'm not reading the whole thing. So this is matching, word and AX matching. So always you have to have the destination and you have to have the size that you need to read. That's your move or your add. You can also add or subtract. And then you're going to have the PTR and then you're going to have the source. Okay, so this is, I'm sorry, this is going to be your destination. This is going to be the size, just to make it different, PTR, and this is going to be your source. Okay, so if you give me the source, I don't care about its size. How much you want to read from the word? I want to read a word. What if I want to move this to an AL register? If I want to move just 7, 8 to an AL register, I would say move to AL, and then I would say what? Byte. And then I would say PTR, and then I don't care about the size anymore. I would say my double. So it's just going to read 1 byte. You see it? So the PTR is going to allow you to read what? To read parts, okay? Access part of a variable. If you want to access part of the variable, you can use it, okay? So you will see the example right here. So this is the whole thing. When you use word, you're actually reading this because this is little endian. This is how the value is going to be stored, okay? So PTR is very important, right? So, and this is something that we're going to look at in this example right here. So right here, you said move, again, that's the syntax. You're going to tell me the amount that you want to read. That is the size. And then you're going to give me the operator, which is PTR, and this is going to be the memory, the source. It's usually memory. And then, of course, you want to read a byte, and you're going to move it right here. Since this is a memory, right, and we have it right here, this is your first byte. Okay, you are reading my double. If you say my double plus whatever, I would understand, but you say my double. So this is going to be the byte on the top. You agree, right, guys? 3, 4, and 1, 2. So you are reading this byte to AL. Okay, so this is what you're going to see, 7, 8. You see it? So the critical part or the most important part, and when you answer questions for PTR, if you don't know how to draw the memory, you cannot answer any question you related to the PTR, okay? Or related in the memory access in general. So you need to really be very good in terms of drawing the memory, okay? So how about this one? So here you said my double plus 1. So this is your double points. Here you said plus 1, then you are pointing here. And you are reading only a byte. So you expect AL to have what? 5, 6. Let's see if we are correct. Yes, it's 5, 6. Okay, so what if you say, I still need to read a byte, but I want to read my double plus 2. PTR, it doesn't care. It's going to go here. It's going to say 0, 1, 2, 3. So this is 2. It's going to read this one. So 3, 4. I'm expecting here to have 3, 4. You see it, guys? So what if I said my double and I'm saying word? If you just say my double, is going to start reading from here. So expecting AX to first read what? 7, 8, that's 0 to 15, right to left, and then 5, 6, right? So expect AX to have 5, 6, 7, 8, right? So that's correct. Okay, what about if I say my double plus 2? If this is 0, 1, I'm right here, and I'm reading a word. So we're going to read 3, 4, 1, 2. So it's going to be 3, 4 first, and then 1, 2. Then you can read it in English now, okay? So we are expecting 1, 2, 3, 4, and that's correct. You see what I'm talking about, guys? So this is very something that you need to keep in mind, okay? Also, PTR can combine actually smaller data type. Okay, so if you have two words and you want to combine them into one new word, you can actually do that, right? So what you're gonna do here, you're gonna say, I want to read the word. PTR, start from word list. So this is my word list. Let's draw the memory again. Without drawing the memory, you are not going to be very successful. So this is word number 0, right? 3, 4, 1, 2. This is word number 2. And you said, I want to start reading from word list. The word list is pointing right here. How far you want to go? You said, I want to go the word. So if you have your EAX register, the first thing you're going to read is what? 7, 8. Because this is 0 to 31. And then what? 5, 6. And then what? 3, 4. And then what? 1, 2. So this is what you have right here. Run this in Visual Studio and see what happens, okay? Pointers, I already explained them. So you can access the parts and then you can do the pointers. I just told you right now when we talked about the A variable, right? So now you are saying array W. So if you say array W, you are assigning the address to this. So you don't need the offset anymore. Do you see it? You don't have the offset. So the equivalent of this, you could have said move to ESI, what? Offset, what? My PTRW. So instead of saying this, you took off this one. And you declare a variable right here. Yeah, declaring a variable right here as a pointer. And you move the pointer right away to ESI. So the ESI now, this is equivalent to this, okay? And then now you can access this memory. You say move to AX ESI, right? So you're gonna move this 1,000 to the AX. You see it? So that is what the pointer is for. So this is what I said right here. I explained that already. This is a very important example. Again, before you answer, that's my advice. Draw the memory to avoid any problem. You're gonna be really tricky. So if I want to draw this memory, I will have 10, 20, 30, 40. That is memory what? My byte points here. Okay, and I know that this is 0, 1, 2, 3. I know it. And then after that, I have another memory. It's going to be a word memory. So what is this? 8A. So I said 8A. Usually, you guys going to say this, and then you're going to write 3B. That's wrong. Remember, this is a word memory. So 8A and then what? 0, 0. Keep that in mind. Okay, and then you're going to go to this one. 3B, 0, 0. Declare this in Visual Studio, and you will see what I'm talking about. So this is my word. It points right here. So this is 0. This is 2. And this is, again, this is going to be what? 7200. You see it? And then it is going to be 4400. Okay, so this is going to be 4. This is going to be 6. And then we're going to have 6600. Okay, and then I'm going to have this D word. So again, this is going to be my D word memory. And I'm going to have 1, 2, 3, 4. So this is going to be 0, 1, 0, 0, 0, 0, 0, 0, and so on and so forth. So draw the entire memory. Remember, this is a pointer. So you say my double. So this is your double. You assign it to my pointer. So you have two references to this memory. Either you can use my doubles or you can use my pointers. Okay? So if I ask you, let's say, just to figure out what is PTR, you see it here, PTR, my words, right? Okay, so this is my word, and you say PTR, and you want to read what? The size D word. So if it's a D word, it's going to start from here up to here, right, guys? You see what I'm talking about? So EAX right here, if this is your EAX, okay? So first we're going to have what? 8A, and then 0, 0, and then 3B, and then 0, 0. My students usually, if they don't do it in this way, they're going to tell me 8A, 3B, 7244, which is wrong. So declare this in Visual Studio, run it one by one, and it's going to give you the answer. Okay? The only thing that you need to think about is that you're going to say, hey, I don't understand. I know this is the right answer, but I don't understand it. Then please stop by during the office hours, and I'll be very happy to help. Remember here we are using the offset. We can get rid of it, right? We can use my pointers right away, right? But we are using offset and my pointer just to show you different way of accessing the memory, okay? So play with this example, please, and try to assign the values right here, okay? All right, so these are other types as well. So now we're done with mainly like the critical operators. So these are like very straightforward types, like type operator is gonna give you the size of the type. So you're gonna say type of var1. Since this is a byte, it's gonna return 1. So EAX is gonna has a 1, 0, 0, 0, 0. Gonna have this part, right? 1, 2, 3, 4. Okay, if you're going to say type of var2 is going to return 2 because this is a word. So it's return the type, right? Just the value in terms of value. See, quad word is going to return 8. Okay, this is the length of. Okay, if you give this less, then you say, what's the length is going to be 3. What's the length of this word? So we know it's 30. So we know it's 30 by 2, right? So 30 by 2. You with me, guys? So this is going to be what? This is going to be 30. It's going to be 30 elements, right? And we're going to have what? Another 2 elements. We are talking about number of elements. Each of size what? Each element of size 2. You see it? So this is element 1, element 2, element 3. We are not counting the number of bytes. We are counting the number of elements. So we have 30 elements here plus what? Plus 2 of size what? Of size 2. How about this part? So this is array word, and we have 5, right? Right, guys? So we have a size, a memory size of size 2, and how many of it? We have 5, right? And then in this part, we have 3. Inside this one, each is having a 3 duplication. So 3 by 5, we're going to have a 15. Okay? On this part, we're going to have how many elements? Length of this? 1, 2, 3, 4. Okay, and how about this part? How many of it? It's 9. Why? Because this is an ASCII. Every character is a 1 byte. So this is 1, 2, 3, 4, 5, 6, 7, 8, and this is 1, so it's going to be 9. So the number of elements is 9. Okay, so this is what I'm talking about right here. All right, so this is going to be the length of. All right, the size of, it's the opposite. So the size is going to give you the number of bytes, okay? So if you talk about the number of bytes right here, so number of bytes is going to be what? Is going to be 3, right? The number of bytes right here, that's different now. The number of bytes, we have 30 space by 2 is going to be what? Is going to be 60, right? And this is 2 bytes plus 2 byte 4. So it's going to be plus 4. So it's going to be 64. Do you see what I'm talking about? This is a D word, right? So if you talk about this D word in terms of size, so each is a 4 bytes. So 4 by 4 is going to be 16. You see it, guys? Okay. So there is a common mistake or a common trick in x86. So if you say, what is the length of this array? 1, 2, 3, 4, 5, 6. And what is the size? So 6 by 2 is going to be 12. That makes a lot of sense. But right here, if you say, what's the length of this array, is going to tell you 2. But we have what? 1, 2, 3, 4, 5, 6, right? Why? First, we have this way of writing the word, and we don't have a comma. If the comma is not seen right here, then they know that these are 2 different spaces in the memory. So the length of is going to be tricked right here because it looks for the comma as the terminator of the end of the array, okay? So that's tricky. Pay attention to that, please. All right, so with that, now we understand what is memory addressing mode, direct with offset, indirect, and indexed, and also we learned the pointers, all right? And we also learned about the PTR operator and how to read the parts, and offset in terms of how to read the register, the memory address right away. Okay, so with that, we're gonna stop right here. I give you some time to play with, and please try to refer to the exercises in the book, and I will also post exercises for test 2. So hopefully with that, you're gonna get the idea with the lab as well, of course, lab 4. You're gonna put it all together, okay? So thank you for now, and see you later. Thank you, guys.